Okay, I've had a lot of coffee, but I'm going to try to do this. I want to talk to you a little bit about the Reynolds number, go over what we went over in class, and kind of use it to demonstrate something with dimensions and what are called dimensionless numbers. So I showed you in class on Friday a video of the Reynolds experiment that looked at the transition from laminar to turbulent flow. This is a dumb sketch of that experiment. So first off, let's just pay attention to my little drawing here. This is a cross section through a duct with flow coming in from the left and flow going out from the right. And that flow can have some average velocity u, right? And that flow will also have a density rho. And the duct itself has some depth to it, which we will call d. Okay, if this was an open channel flow, that would be depth. If this was a pipe, it would be the diameter of a pipe. So what happens during in the Reynolds experiment, the original experiment, is that the flow is coming in from left to right and it's going very slowly. And this little tiny tube has a little bit of dye that is being injected. And for very low velocities, that dye comes out and it flows along as a nice line like this, right? And that would be laminar flow when velocity is very low. What would happen as you increased velocity is it will start to become wavy as it exits, and then as it comes faster still, it will start to shed vortexes as the flow comes out. Vortexes get shed off like this, but there's still some pattern to the flow. It's not fully turbulent yet. And then what would happen as I take my little vortices out is that the flow would come. Actually, let me do those vortices again. It would come out like this, and these vortices would be shed like that. Okay, and then the flow would come out, and these vortices would start to get very complicated, right? And they would start to get messed up, and then eventually they would come out, and the flow would just become completely chaotic. You would not see any order to it, right? And that would be fully turbulent flow. And what uh, Reynolds realized is that this must somehow be controlled by the properties of the fluid. Like I said, the velocity, the density, and the depth, but then also the viscosity. Okay, and these are the dimensions of those important units up here. And Reynolds wasn't like doing anything special here. He just wanted to find a general state that described when this would happen that would be true for any state. And so what he did is he came up with what we call a dimensionless number that we can now call the Reynolds number. And what's important is that it is dimensionless. It has no dimensions. And I'll explain what that means. Remember that it is rho u d over mu. And we could look at this as the driving forces, the forces that drive flow, over resisting forces, the forces or properties that tend to resist flow. But now let's look at the dimensions of this, okay? We're going to go through, we're going to put the dimensions in. So the Reynolds number, dimensions of rho are mass over L cubed, right? Dimensions of velocity are L over T. The dimensions of depth, as you see over there, are L, all right? And this is all divided by the dimensions of viscosity, which is mass over length times time, okay? But if we actually go to simplify this, we're just going to move the denominator up. I'm going to rewrite this as mass over length cubed, length over time, length, right? So that's the whole numerator above there. And remember that division of a fraction is the same as multiplying by its inverse. And so we put LT over M. You may not remember that, but you will now. And watch what happens to the units. Mass and mass cancel. Length, length, and length cancel length cubed. Time cancels time, and it is dimensionless. Other dimensionless numbers that you know of, any percentage is a dimensionless number. Anytime you divide one thing that has the same dimensions by the other, it becomes a dimensionless number. They're useful because you can compare different systems if they have the same dimensionless numbers. So remember the upshot of this is that Reynolds numbers approximately equal to 500. That is when you get the transition from laminar to turbulent flow.